The proton gradient formed across the inner membrane of mitochondria when electrons move down the electron transport chain fuels ATP synthesis. ATP synthase, the main source of ATP production, has two major subunits, F0 and F1. The F1 subunit is comprised of alternating alpha and beta chains surrounding a central gamma chain. The beta chains catalyze the formation of ATP from ADP and an inorganic phosphate. The gamma chain connects the F1 subunit to the F0 subunit. The F0 subunit is made of A, B, and C chains and is responsible for the transport of protons across the membrane. The 10 to 15 C chains, depending on the species, assembles to form a C ring. The C ring rotates with the flow of protons through ATP synthase. Two of the 10 C chains are isolated from the surrounding lipids by the A chain. Key aspartate residues of these two C chains lie in contact with the two hydrophilic half channels of the A subunit. The P-side half channel is open to the intermembrane space, while the N-side half channel is open to the mitochondrial matrix. The A subunit also has a positively charged arginine residue, whose position shifts between the two half channels. The key aspartate residue facing the P-side half channel is initially deprotonated and thus negatively charged. The position of the C ring is stabilized by an electrostatic interaction between the negatively charged aspartate residue and the protonated arginine from the A chain. Rotation of the C ring in this state would be unfavorable, since the negatively charged aspartate would come into contact with hydrophobic phospholipids. The key aspartate residue facing the N-side half channel is protonated and thus neutral. The proton gradient drives the rotation of the C ring by protonating the negative aspartate. The relatively high concentration of protons in the intermembrane space facilitates the entry of a proton into the P-side half channel. Repelled by the proton, the arginine residue shifts toward the N-side half channel, allowing the negative aspartate residue in the P-side half channel to bind to the incoming proton. The positively charged arginine in its new position triggers the deprotonation of the adjacent aspartate, and the proton is released into the N-side half channel and out into the proton pore matrix. With few protons from the matrix available, the reprotonation of this aspartate is unlikely, and now the C ring is free to rotate by one C chain. The rotation moves the deprotonated aspartate toward the P-side half channel and shifts arginine back to its original state, restarting the cycle of proton import from the intermembrane space toward the mitochondrial matrix. The rotation of the C ring is ratcheted, where each movement of a proton across the membrane corresponds to the rotation of the C ring by one C chain. The rotation itself is a result of Brownian motion, but the directionality of the rotation is determined by the difference in proton concentration across the inner membrane. The rotary motion of the C ring drives the rotation of the gamma chain that connects the F0 and F1 subunits. Due to its structural asymmetry, the gamma chain interacts differently with each of the three catalytic beta chains. When the gamma chain is in a given position, the three beta chains adopt different conformations. For each 120-degree rotation of the gamma subunit, each of the beta chains switches between three different conformations. These sequential changes of conformations are necessary for the synthesis of ATP from ADP and inorganic phosphate.